going to look at rational functions today. Rational functions are functions where you have a polynomial over a polynomial. So basically kind of fraction problems. Now we're going to find these 5 features of these equations, and we're going to use those to draw the graph of the function. So to find the y-intercept, this is like you always do. You make x equals 0, and you write this as a point, so 0 comma some number, right? And then we're going to find the horizontal oblique asymptotes. This is going to be based on the powers or degrees of your numerator and denominator. And we'll talk about how you find that. An asymptote is a guideline. So what's going to happen is we're going to find some kind of line. That's going to be a guide. It's going to usually be a horizontal line, but sometimes it'll be a diagonal. And your graph is just going to come up and kind of get close to it. And it's going to follow it. It's going to help you draw the picture. X-intercept, what we're going to do is we're going to look at what, actually let me say it this way. For this we're going to find the zeros of the numerator. So what makes the top 0? Because like normal, you'd want to make your fraction equal to 0 if you wanted to find the x-intercepts. But if you have a fraction and you want that fraction to be equal to 0, then what that means is you want the top to be equal to 0. So you don't want the bottom to be equal to 0 to find out a value of 0. Okay. Now, where the bottom equals 0, these are the vertical asymptote. So zeros are the denominator. And one thing to keep in mind, I guess I should say, these are always going to be y equals something, maybe y equals mx plus b or y equals b. These are going to be some number comma 0 for an x-intercept. These are always going to be x equals a number. So x equals some kind of number. And then, so these are vertical lines, vertical guidelines, so you can think, and so your graph would kind of approach one of those. Now, horizontal guidelines we can touch. Vertical guidelines, vertical asymptotes, never can touch, because that's what would make you divide by 0, so you can't ever touch those. And then points of discontinuity, these occur where you have factors that cancel out from the top and bottom. So we'll look at one example of that in this video. And then we're going to use that information once we have that to help us draw the graph. And you're going to have to do some, maybe a little bit more analysis, kind of logic think through the thing and see if we can figure out what the graph looks like. But let's get started. All right, so I'm going to start by looking at, let's find some y-intercepts, right? If there are any. And so, again, the way you find the y-intercept, you make all the x's 0, and you see what happens. And so in this case, we're going to get 1 over 0, which is undefined. What that means is we don't have a y-intercept, and you don't always have a y-intercept. Sometimes you do. Most of the time you do, but not always. In this case, I make all the x's 0. And let me say, you don't necessarily have to go through all this work that I'm showing here. I'm just trying to show why the answer is going to come out that way. So everything with that is 0. I'm going to get these, which are going to come out to be positive 4/3. So 0, 4/3. Remember, y-intercepts are points, so please write them as points. And then this one, make all the x's 0, and you're going to get 0 over -1, which is 0, and that's okay. You can have 0, 0 as a y-intercept. Nothing wrong with that. So you can have 0 on top, but you can't have 0 on the bottom. 0's on the bottom, it's undefined. And so therefore you don't have a y-intercept. 0's on top, that's okay, as long as the bottom isn't 0. That just means you go through the origin. All right, so now let's go to the horizontal or oblique asymptotes, right? And so what we're going to do is we'll look at the powers. So that's what I said. We're going to look at the powers. So on this one, what we're going to notice is the degree or the power of the denominator is larger than the degree of the numerator. If that's ever true, that you have a higher power on bottom than you do on top, then this is always going to be y equals 0. And these are horizontal lines for the first two, and then this third one we're going to have a diagonal line. So it's always going to be y equals a number when it's a horizontal line, or y equals mx plus b when it's a diagonal line. This one, on the other hand, this one, the powers are the same. And so if the powers are the same, then what you do is you look at these leading coefficients. And be careful, you notice like the leading coefficient here is -2, not 1. It's not what's the first thing written, but what's with the highest power of the variable in the numerator or denominator. So here these are written in the right order. So 2 and 3. So this is going to be y equals 2/3. So let me see if I can explain what's going on here. What we're looking at is what is the graph going to, what values of the graph going to approach in the long run. And in the long run here on this top one, if you put like, let's say 1,000,000 in here for x, well, this is going to be, you know, that 1 isn't really going to matter at all. What's going to matter is this -2 million. You know, -2 times 1,000,000, so -2 million. And that seems like, okay, -2 million, that seems like a lot. Until I look at the bottom and I realize that here I have 1,000,000 squared, so 1,000,000 millions. So I'm looking at -2 over 1,000,000 in effect. And what happens with a fraction is that as the bottom gets bigger and bigger, the whole value of the fraction gets smaller and smaller. And so in the long run, this thing's going to approach a value of 0. It's going to be basically 0. You know, you're going to have such a tiny number. It's going to, in effect, be 0. So this graph is going to get closer and closer to a y value of 0. On the other hand, if I look at the second one, these two, since they're both squared, they're going to increase at, you know, pretty much a consistent rate to each other, and that rate's going to be the ratio 2 to 3. So if you put like 1,000,000 in here, yeah, you have 1,000,000 million times 2, so 2,000,000 million, and then this is 1,000,000 million times 3, so 3,000,000 million. So that's, you know, in effect, 2 to 3 ratio, and that's what this is going to approach in the long run. Now, in the case of the top being bigger, in this case, the graph's going to go up and up and up and up because the top's going to get bigger faster than the bottom. But it's not random. It follows a pattern, and that pattern is dictated by some kind of diagonal line. And what I want to do is figure out what's the equation. So, you know, the graph is going to follow that diagonal line. What's the equation of that diagonal line? And the way I'm going to figure that out is I'm going to do, in this case, I have to do long division, but I'm going to divide. So if I could do synthetic, I would, but you know, since I'm dividing by x squared, I don't have that option. So I'm going to do long division, and I'm going to ask myself, you know, just how I normally, what do I multiply x squared by to get x to the third? And we multiply by an x. So that's going to give me x to the third times -1, -x. Change the signs, 2x. Now notice this is a remainder because its power is smaller than the divisor here. So in this case, I don't care about the remainder because I'm just seeing what it gets close to. And I get close to the equation y equals x. This line here is y equals x that the graph is getting close to in this case. So you got to divide it out, ignore the remainder, don't care about the remainder. What I care about is what do I get up in this quotient area, y equals x. That's what I'm looking for. Okay, so diagonal asymptote to horizontal. What does it look like in the long run? That's what you're figuring out when you're doing that. All right, for the next ones, what I want to do here is I want to factor before I move on. So this first one, there's nothing really to do here. It's already, that's pretty much it's factored down. I mean, I can do some stuff, but it's not really worth my time. So I'm going to factor these other ones. So 2x squared minus x minus 2. Take out a 3, x squared minus 1. So this will factor as 2 times x minus 2, x plus 1. This will factor as 3 times x minus 1, x plus 1. Those will cancel out, giving me 2 over x minus 2 and 3 x minus 1. And then this one, this will factor as x times x squared plus 1. This one will factor as x plus 1, x minus 1. This is the sum of squares, so it's not going to factor out anymore how we normally talk about factoring out. So, you know, we're going to stop there. And now I'm going to talk about the other ones. All right, so next thing I want to look at here is the x-intercepts. And where the x-intercepts occur is what makes the top equal 0. So I'm going to look at this one, maybe add the 2x to the other side, divide by 2, So 1/2 comma 0. Again, remember x-intercepts are points, so please write it as such. So I'm looking at the top of this one equals 0. Well, it's obviously 2 can't equal 0, but x minus 2 can. If you add the 2 over, you get x equals 2, so 2 zeros in x-intercept. Here, if we set x squared plus 1 equal to 0, and you subtract a 1 over, you get x squared equals -1, take the square root. These are going to be plus or minus I, so again, not real. I don't really care about that part. But this part, x could equal 0, in which case I have 0, 0, and you go, well, yeah, sure, of course, because I got the y-intercept to be 0, 0. I have to get the x-intercept, at least one x-intercept to be 0, 0 as well, since the origin is on both of those. So what makes the top 0? That's what you're looking for with the x-intercepts. Next thing we want to look at is the vertical asymptotes. So vertical guidelines. And what we're going to do is look at what makes the bottom equal 0. So what makes x squared plus x squared equals 0? We'll take the square root. X equals plus or minus 0. So what that tells me is I have x equals 0 and another x equals 0. And the fact that I have two of these is kind of important, and we'll see when we start drawing the graph that it's good that I recognize that there are two vertical asymptotes that are just right on top of each other. This one, if I'm looking at what makes the bottom equal 0, well, x equals 1. That's what makes the bottom equal 0. You can put 1 minus 1 in there. And then on this one, if I look at what makes the bottom equal 0, it would be -1 and separately +1. These are vertical lines. Vertical lines are always x equals a number. So that's why I want to say x equals -1, comma, x equals 1, not x equals -1, comma 1. I'm not looking for numbers. What I'm looking for is equations. So these are two totally separate equations there. So now, let's say you find the vertical asymptote, what makes the bottom 0. Now I'm going to look at any points of discontinuity. And these occur only where things cancel out. So you notice here I have the part where I factored in and did some canceling. That's going to be important. This one, none. I didn't do any canceling. No big deal. Don't have a point of discontinuity. This one doesn't have one either. This one does. And so we're looking at a point here. And that's what we're looking for. It's some point, and what's going to happen is the graph is going to come up to that point, and it's going to, the rest of the graph thinks that point's there, but it actually isn't. It's actually an empty spot where there is no graph. And so what I need to do is figure out where that location is. Now the x value of that location is going to be the 0 that corresponds to this canceled out factor. So in this case, is a 0 of 1, -1, 0 of -1. So that's going to be my x value. X is going to equal -1. Now to find the y value, what I want to do is, even though I said this is an equal sign here, I can plug -1 into this statement, and I can't plug -1 into this statement or this statement before I did the crossing off. If I did it in either one of these two, I would have gotten 0 divided by 0, which is undefined. You know, again, same here, 0 divided by 0, which is undefined. But I can plug -1 into here. So everywhere else on the graph, this statement, this factored and canceled out version, is equivalent to this original statement, except for this one spot. And so I want to figure out where is that one spot at. So I'm going to put the x value in here for these x's in the end result. So this is going to be 2 times -1 minus 2 is -3. 3 times -1 minus 2 is -2. So -6 over -6, or 1. So this has a point of discontinuity at -1, 1. So the graph's going to come up to there and just skip over it. Normally on this graph it would go right through it, but because this factored and canceled out version isn't really what we're doing. We're doing the original problem. That's why we have this point of discontinuity. All right, so let's kind of put all this stuff together. Let me grab all the information we know here, and we're going to use this, and we're going to draw some graphs. So on this first one, no y-intercept, horizontal at y equals 0, x-intercept at 1/2 comma 0, x equals 0 are vertical, and no point of discontinuity. So I'm going to start drawing my picture. So I don't have a y-intercept, but I do have a horizontal guideline at y equals 0. That's right on the x-axis. I go through the point 1/2, comma 0. So you say, oh, I touched that guideline. It's okay to touch the guideline if you have to. I would prefer not to, but if I have to, I have to. Now these vertical guidelines, no, you can never touch those. And that's all I have. This is probably going to be the hardest one we're going to draw today. So what I'm going to do is to figure out what this looks like. Let's talk about some possibilities of things that could happen. You could have, just following these guidelines over here. I don't have any guiding points, so I'm just going to kind of wing it. And I'm going to say, okay, that curve could look like that. Or, alternatively, that curve could look like that. Now, it can't be both, because it wouldn't pass the vertical line test. These are functions, so it would have to pass it. So it can be one of these. I don't know which one. Now, over here, this curve, I got to follow these guidelines, but I also have to go through this point. So, maybe I come up, and I cross, and I kind of go out over there. Or, alternatively, maybe I start high and I kind of come down and go through there and then follow out that way. So, I got to cross over. So I need to figure out which of the, what's what. So the way I'm going to do that is I'm going to say, let me pick a really big positive number way over here on the side. Okay, so I'm going to pick a really big positive number over somewhere off this graph here. And I'm going to plug it into this problem. And what I'm going to do is I'm going to look for what's the sign of the answer. I don't really care about the value. I just want to care about the sign. So if I put a big positive number in here for x, this is going to be -2 times a big number. So basically it's going to be a negative number. And then you're going to square that number and it's going to be positive. So a negative divided by a positive is going to be a negative. So as I go this way, I'm going to have to be in the negative y values, which means I have to be this blue line. I can't be this green line. So I'm going to go ahead and erase that green line. That's not going to be a possible answer. Now, what normally would happen here is when I come to a vertical line, normally I would go up on one side and down on the other side. So my first instinct is to say, it's got to be this graph. But if I actually put this in my calculator, what I'd find is, no, it doesn't do that. Instead, what it does is it actually goes up and up. And you say, well, how would I know that? How would I possibly know that? Obviously, from what you just said, usually it alternates. It'll go up on one side of this vertical line and down on the other. Why is this going up and up? Now, the reason I know in this case it's going to be going up and up is, oops, because I made a mistake here. There's another vertical asymptote, x equals 0. Remember we said, take the square, set this equal to 0, take the square, you got plus or minus 0. So there's 2 of these vertical asymptotes. And so what happens is normally you would switch, so I'm going up, so I would switch to go down, but then I'd switch a second time as I'd go up. So normally this would go up and, up and down. Now it's going up and up because there were 2 identical vertical asymptotes. So that's why it's important that you actually, kind of let yourself know that when you're doing this. So this is probably the hardest one. Again, you can always use a graphing utility or something if you really get stuck and you're not sure about what's going on. But you should plot all this information first and then, make an effort to try to figure it out. All right, so let's look at this one. So, again, A, B, C, D, E. Here we had a y-intercept at 0, 4/3. Y equals 2/3 was our horizontal. 2, 0 was an x-intercept. X equals 1 was a vertical asymptote. And then we had this point of discontinuity at -1, 1. So we're going to plot all this information that we have. So this is 1 1/3, so 0, 1 1/3, somewhere around there. Y equals 2/3, so some kind of height like this. And I think this one's going to end up being like one of the easier ones we're going to graph. 2, 0 is my x-intercept. X equals 1. That's my vertical. And then we have this point of discontinuity at -1, 1. So what that's telling me is I have an open circle there that I approach, but I don't actually touch. Okay, so think about like this, like little dash is like a road. So I'm on the road, I'm following the road, and I need to stop at, one of my friend's house, but nobody's there. So then I go over to my other friend's house. How you doing? And then I get back on the road, and I'm going to go down that path down there. Now, well, like I said, usually what will happen on one of these vertical lines is on one side you'll be going up, the other side you'll be going down. And it doesn't always happen, especially when you have the double roots, or double zero. But in this case, we only got x equals 1 as a vertical asymptote once on the bottom. So I'm expecting that, and if I look at, follow the dashed lines, go through there, that makes sense. I'm on the road, and then I gotta stop by somebody's house, and then follow the road out over there, and actually try to go through the points there when you're drawing it. Hopefully you're doing a little bit better job than I am with this. Should stay underneath that dashed line. I'm just having a hard time with this pad, but you get the idea. It looks something like that. And again, you can put that in your calculator. If you're going to put these things in your calculator, make sure you put the numerator and the denominator in parentheses. You're going to type it in just to be safe, and you get that to look right. Okay, so let's look at this one. So this is the third one, A, B, C, D, E. So what do we know? We know we had a 0, 0 there. This had a diagonal asymptote at y equals x. Of course, the x-intercept has to be 0, 0 if the y-intercept is 0, 0. And then we had two vertical asymptotes, two totally separate ones, and then no points of discontinuity. All right, so we got a y-intercept at the origin, which is also the x-intercept. And then we got a line, y equals mx plus b, so 0, and then a slope of 1 over 1, so up 1 over 1. So this is going to be a diagonal guideline right on that 45-degree angle there. Okay, I already did that, 0, 0, so verticals, boom, 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 boom. Okay, have this. Now I want to draw some graphs. So again, let's think of some possibilities here. I could have a curve, following these guidelines. I could have a curve that does that. Or I could have a curve that, kind of is in this triangular region. So it could be in this trapezoid type region. Whoops, what happened? It could be in this trapezoid type region, or it could be in this triangular region. And I actually know which one of those that is by the process of elimination, by knowing what it's not. So let's assume it was the bottom one. It was going along and following this path when all of a sudden, here's the x-axis. If I'm on this path, then I would need an x-intercept right here. There isn't one there, so I know it's not this path. It can't be, because I don't have an x-intercept, which means it has to be up in this area. And same idea here, I could look at this side and say, oh, I'd have to, if I was following this curve, I'd have to hit the x-axis somewhere. I'm not, so therefore, by process of elimination, it's got to be, something like this. Then I come to the middle, and the middle is a little bit, iffy. Hard to know what's going on here. But if I think about, that alternating on these vertical lines, since I'm going down here, I'm most likely going up here. Since I'm going up here, I'm most likely going down on that one. And in the middle, I have to go through this x-intercept. So I'm going to go down and kind of do a little shimmy and go down that way. So it's probably going to look something like that. And again, you can check that if you want to put that in your calculator. Again, put parentheses on there. So that's rational functions. That's what we're going to look at, finding those intercepts, and then using those to graph, or those different features, x and y intercepts, or asymptotes, and any points of discontinuity, and then using those to draw our graph. And you can use your graphing calculator or a graphing utility to help you draw that, but please take, you should plot all the information first, try to figure it out on your own, and then use the calculator as a backup.